When there is a traveling of the charges from one place to the other, there is a generation of the current. When there is no movement of any charges, then it is clear that the work done is said to be zero. Dielectrics is a one inside which there is no presence of charge, but the electric field, that is electrostatic field, is present over there. Protecting the object or a conductor by the influence of any other external electric field is said to be electrostatic shielding. Hello everyone, I'm Vrinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to Session 3 of Chapter 2, Electrostatic Potential and Capacitance. So in today's class, we are going to discuss about the electrostatics of the conductors, dielectrics, polarization concepts. So in electrostatics of the conductors, we study that the substance which carries electric charge from one place to another place is said to be a conductors. That means the conductors are the one which conducts electricity. So, what exactly the conductors carry? The conductors carries the charges which are responsible for the electric current to pass through it or the electric field to pass through it. So, that is all about the conductors. It's very easy to define the conductors, that is the conductors are the one which conducts electricity. That means there is the traveling of the charges from one place to the other. When there is a traveling of the charges from one place to the other, there is a generation of the current. So that is all about this conductors. So here we study about the electrostatics of the conductor. So what is meant by electrostatics? Electrostatic means the charges which are at rest, the charges which are in stationary position, and the electric current which is produced due to those static charges. So that is all about the electrostatics of the conductors. And under that we study the first point, inside a conductor the electric field is zero. While doing the first chapter, we had studied regarding the Gaussian surface in an infinite long straight current carrying wire as well as the sheet and a spherical shell. During these times, I had told you that electric field inside the conductor is zero. So that is a concept, that is inside a conductor, the electric field is said to be zero. So why is it called the electric field inside the conductor is zero? Suppose if you consider a conductor is the one which has got C of delocalized electrons. So the conductor is the one which has got C of delocalized electrons. Okay. So here, suppose if you consider an external electric field which is passing this is the direction of the electric field. This is the direction of electric field. So just name it as EA. If EA is the applied electric field, and now you consider a conductor which contains delocalized electrons, C of delocalized electrons, that is, place this conductor in between this. So you're placing the conductor over here which contains, so the applied electric field is from positive towards negative. And you have C of delocalized electron which is present between this conductor. So those electrons get attracted towards the positive charge of the applied field, that is, these pair up. Negative charges resides near the positive charge and positive charge resides near the negative charge. So you can just pair it up in this way. Okay. So now when the electric field which is passing through the conductor and within the conductor there is the electric field which moves from positive charge towards negative charge, because as we have studied, the electric field lines are the one which moves from positive to negative. So external field is from positive to negative, internal is from positive to negative. So our external electric field EA, that is applied electric field, is in this manner, and your internal electric field is in this manner. Okay, so now both are the electric fields which are having equal magnitudes, but the direction is opposite. Electric field is a vector quantity. Its direction is opposite to each other with the same value, that is the same magnitude. When that is the case, both the electric field gets cancelled out, and then what remains is 0. The electric field inside the conductor is said to be 0. Only the externally the electric field can be seen, but not internally. Internal of the conductor has got 0 electric field in it. That is the explanation for this point, that is inside a conductor the electric field is 0. Why? This is the concept which I have represented in a diagram. Okay, so the next point is, at the surface of the charged conductor, electrostatic field must be normal to the surface at every point. As we have studied, that is, for a conductor, the electric field should always be at 90 degrees. So let us see how exactly it is going to be 90 degrees. So suppose if you consider a conductor and just consider there are charges on the surface of the conductor, okay, and suppose you give just a push to a conductor along its circumference. So the charges pushes one another and it moves, and these undergo push, which is said to be impossible practically. So what is the thing? Consider a electric field at a point P over here. Consider a point P over here, because we can't consider each and every place. Consider any point in a diagram, and suppose that there is an electric field to it. You will have to resolve one electric field to 2 points. Suppose if this is a tangent drawn to a circumference, and resolve this factor into 2 units, say one arrow towards y-axis, one arrow towards x-axis. So this y-axis is called as E sine theta, and your x-axis is E cos theta, wherein this vector will be a resultant, that is vector E. And now, in order to get cos theta, consider E cos theta, which is considered to be 0. Because this factor, the resolved component is considered as 0. Then, in order to have cos theta as 0, what should be the value of this theta? That is the angle. It should be cos theta is 0 when theta is 90 degrees. So cos 90 is said to be 0. So what is that 90 degree? It is known as either radial, or else perpendicular, or else normal. That means the electric field, angle of the electric field on the surface of any conductor should be 90 degrees. That is, it should be normal or radial or else perpendicular. So that is the explanation for this concept. Next we are going to, the interior of the conductor can have no excess charge in the static situation. Okay, when you consider a conductor, within a conductor we have already discussed, that is, within a conductor, suppose if this is a conductor, and at the center of the conductor, that is within the conductor, there is no charges. If there is no presence of the charges, there is no movement of the charges as well. If there is no movement of the charges, then it is clearly known that there is no electric field within the conductor. That is, inside the conductor, there is no presence of the electric field. Outside the conductor, there is presence of the charge, which is responsible for the electric field. That is the explanation in this. And next we are going to Electrostatic potential is constant throughout the volume of the conductor and it has got the same value as on its surface. That is, within a conductor, there is no charges which is present, which is said to be there is no electric field inside a conductor. Inside a conductor, the electric field is said to be zero. Okay, so outside the conductor, there is a presence of charges. And there is no work which is done in moving a charge from one place to other. That is, we are talking about the static conditions. Static conditions means there is no movement of any charges. When there is no movement of any charges, then it is clear that the work done is said to be zero. If the work done is zero, then according to the definition, the potential, that is electrostatic potential, will also be zero. That means there will be certain potentials at each and every point, and when there is no movement of any charges from one place to the other, the electrostatic potential doesn't occur over there. That means the electrostatic potential is said to be constant throughout the surface at each and every point. So that is all about electrostatic potential is constant throughout the volume of the conductor and it has got the same value on its surface. It is all about value as on its surface. So this is all about your electrostatics of the conductor, and finally we are getting into the electric field at the surface of the charged conductor. And what is that? The electric field at the surface of the charged conductor is given by vector E is equal to surface charge density divided by epsilon naught, and in order to equate this vector quantity, it is a unit vector. So how do you get this? As you all know, just consider a conductor, a free diagram upon which the charges are present. And you consider a point P, because we are not considering any interior of the conductor. Just consider a point P where exactly you are calculating your vector E. In order to calculate an electric field in a point P in any of the surfaces, you will consider Gaussian surface. So suppose I consider a cylindrical Gaussian surface which is given by this dotted lines, and ds will be the area of it and E will be the normal vector which is normal to the surface of the conductor, that is the electric field. Now, by looking at this diagram, the flux through the point P, the flux is given by the figure. The flux is given as vector E into ds, that is electric field per unit area. Electric field in that area is said to be flux. So you can just give electric field into the displacement ds. So now we have this flux with us, and we all know that is we are talking about the surface charges. So according to surface charge density, we have charge per unit area. So area is supposed to be ds here. So what happens to the charge now? Charge Q is equal to, we have sigma into ds. So call this as equation 1, and this is a charge which is having sigma into ds as the equation. And now consider Gauss law, because you are considering the Gaussian surface to calculate it, and according to Gauss law, the total flux through an enclosed surface is always 1 by epsilon naught times the charge which is enclosed through it, so which becomes Q by epsilon naught. So call this as equation 2. Equate equation 1 and equation 2, because its left hand side is the same, that is phi and phi, that is the flux. So on equating, you will get vector E into ds is equal to, your Q is nothing but sigma into ds. So sigma into ds divided by epsilon naught. ds cancels with ds. What remains is vector E is equal to sigma divided by epsilon naught, that is surface charge density, into, in order to balance this, I just introduce a vector quantity, that is a unit vector. So here is the electric field at the surface of the charged conductor is this value, that is surface charge density divided by epsilon naught and the unit vector. This is the equation. So that is all about your electrostatics of the conductor. Next, moving on to dielectrics. So what is meant by dielectrics? Dielectrics concept is nothing but the one inside which there is no presence of charges. Dielectrics is a one inside which there is no presence of charge, but the electric field, that is electrostatic field, is present over there. So dielectrics is a one which faces, that is which undergoes the electrostatic field, but the presence of charge is zero. That means there is no presence of charge within the conductor. Such kind of materials are called as dielectrics. So under dielectrics, we talk about two molecules, that is polar molecules and non-polar molecules. So here we have polar molecules and non-polar molecules. So you can just take the example for polar molecules as H2O, HCl, and in non-polar molecules you can take the example of carbon dioxide and H2. So these are the concepts of dielectrics. Let us move depth into this, that is, let us just explain what is meant by polar molecules and what is meant by non-polar molecules. Coming to polar molecules, so you have already know why exactly inside the conductor the electric field is zero, as we have discussed. That is, the electric field, that is applied electric field, will be equal to the magnitude of the induced electric field within the conductor. So when that is the case, both are having same magnitude with different direction, that means it cancels out each other, because of which within the conductor, that is inside the conductor, the electric field is said to be zero. That means it is the concept of dielectric. So inside the conductor, electric field becoming zero is nothing but the dielectric component. So under that, we are talking about polar molecules now. So what is meant by polar molecules? Polar means there is separation between positive as well as negative charges. Okay, polar means the separation between positive and negative charges, and here polar molecules are the one which shows the polar concepts, that is its polarity, that is its charges, positive charge and negative charges, both doesn't coincide in polar molecules. So you want to see it practically, we can just visualize over here what is meant by polar molecules. Suppose you have taken the example of H2O and consider the same over here. There are three molecules H2O. So this is H, this is its center, this is the center of one molecule, so it is H, and this is the center of other molecule O. So this is positive ion, and here it is a negative ion. So we have H, H and O. H2O is the example which you are taking over here. So the center of two positive ions is this. And here there is a negative ion. How is the flow of electric field in this molecule? That is, if this is the center of both the positive ion, this also will be plus. So flow of electric field is always from positive towards negative. So this will be the flow of electric field. But how is the dipole moment in this? Dipole moment is always opposite to the flow of electric field. That is, dipole moment is in this way, negative to positive, which is P vector. So what can you say in polar molecules? There is presence of dipole moment. Okay, dipole moment exists in case of polar molecules, and there is separation. That is, there is no coinciding of the positive charges and negative charges, which is seen over here. There is no coinciding of positive charges, center of mass of positive charge with the center of mass of negative charge. So that is all about your polar molecules. With the example, you can easily give its difference. Okay, so coming to the other example, if I am taking, let me consider HCl. H and Cl. So this has got H. This is the center of mass of the chlorine molecule. So we have HCl. So center of this positive and negative can be this. So the direction of flow of electric field is from positive to negative, but the dipole moment is opposite to that of the electric field. So there is presence of the dipole moment in case of polar molecules. So now coming on to the non-polar molecules. So just give out what is meant by non-polar molecules. So in this case, you can see the center of mass of the positive charges does not coincide with the center of mass of negative charge was for the first one, that is polar molecules. Now we are dealing with non-polar, which is contrary to that is the center of molecule of positive charge coincides with the center of mass of the negative charge. So suppose if you take an example of carbon dioxide CO2, you're taking one carbon atom and two oxygen atom. So you can just split it up as here there is O oxygen, here there is O oxygen, here there is carbon dioxide which is present at C, minus and positive ion. So here we have positive sign over here, that is at the center. So the center of these two oxygen atom lies at C. The center of the oxygen atom lies at C. Both the oxygen atoms, because of which we can say there is no dipole moment. So the dipole moment, because it coincides, the center of mass coincides, the center of mass of positive as well as negative sign, both also coincides with each other, because of which it is difficult to analyze the dipole moment of these molecules. So there is no dipole moment in this non-polar molecules. So next is, if you're taking CO2 as one example, the other example which I had given was, it was H2. So here we consider two hydrogen molecules whose center coincides over here. So this is H and this is H, because of which you can say there is no dipole moment in non-polar molecules. So that is all about your polar molecules and non-polar molecules under dielectrics. So you also have electrostatic shielding. So electrostatic shielding means, what is meant by shielding? Shielding means protecting. Protecting the object or a conductor by the influence of any other external electric field is said to be electrostatic shielding. Okay, so electrostatic shielding means you are protecting a conductor by the influence of electric field, that is, you're shielding it. Such a concept is called as electrostatic shielding. So now we are talking about polarization. Polarization here is nothing but dipole moment per unit volume of a conductor. It is dipole moment per unit volume of a dielectric. So what is meant by a dielectric? Dielectric is a material which has got the presence of electric field with the absence of the charge. Such a material is said to be a dielectric. When that is the case, what is meant by this polarization? Polarization means within that dielectric medium, we are checking out the dipole moment per unit volume. So dipole moment per unit volume of the dielectric is said to be a polarization. It is dipole moment per unit volume of dielectric is said to be polarization. So, polarization, that is the dipole moment, is directly proportional to the electric field. So, when this is a case, you have P is equal to, removing proportionality constant, you have base E and electric field. This is known as susceptibility. Susceptibility means it shows the lack of ability to resist. So that is all about your polarization concept. So in today's class, we have studied about the electrostatics of the conductor, under which we studied the inside the conductor, the electric field is said to be 0 and electric field is always normal to the surface of conductor. That means which is at 90 degree, and within the conductor, the electric field is 0, and outside the conductor, electrostatic potential is always constant under the static charges. And then we studied that electric field on the surface of the conductor has got certain value, that is E is equal to sigma divided by epsilon naught into n vector. We derived that equation, and finally we studied about dielectrics, types of molecules under dielectrics, polar molecules and non-polar molecules. What is meant by polar molecules with its example, what is meant by non-polar molecules and its examples. Finally, we studied about the electrostatic shielding as well as polarization. So let us all meet in our next session, that is session 4 of the same chapter, with the depth of this concept. Until then, have a good day. Thank you.